What's up YouTube, and welcome back to my channel. How would you like to make your own AI-powered video surveillance device, but without sending any of your sensitive video footage anywhere? Today I'm going to show you how to make a self-contained object detection system using Tensorflow and a $20 Orange Pi Lite. Strap in and let's get started. So let's take a look at what you're going to need. Of course, you're going to need a board. For the purposes of this demo, I built this with the Orange Pi Lite, and I got the set number 9, the one that you can find on the Orange Pi site where they provide you the GC2035 camera. But I also did test this on an Orange Pi PC, and I think it would work with other Orange Pi devices that have the same camera interface. A GC2035 camera, this is the one that I got that came with the set 9 with the Orange Pi Lite, but I think you can also buy these separately. And a DC barrel cable to power it. The Orange Pi Lite and the more powerful Orange Pis can't be powered directly with a micro USB cable, so you will need the barrel input. I like to use this with a direct USB because I have a good 2 amp power supply, and that seems to work well enough. So here I've got all of the parts disassembled. I thought I'd just quickly show you how to put everything together because it wasn't immediately obvious to me how you should connect the camera when I first got this. So of course here we got the Orange Pi Lite board, and these are the parts for the camera. So there's this little expansion board that you plug the camera into, and you plug that into the Pi. This is the actual camera, it's tiny, and the ribbon. And of course, you know, we have our trusty SD card, and as I mentioned in the other video, we are going to need an older version of Armbian to support the camera device. So first thing is, the ribbon has a blue strip on top, or a blue marker on top, on the top end, and then there's a kind of metallic sort of thing here that you can kind of see. So you want to connect that to the top of this thing here. And so that should just sort of go in, and you should feel like a slight little bit of, you know, resistance, not a lot, but just so that it kind of stays in there almost on its own. And then you want to click this thing into place. So that's one end. You need to also do the same thing for the camera. So again, the camera has got some kind of gold connectors there. You'll want to connect that into the expansion board like that and click it nicely into place. Now you've got the camera ribbon ready to go, and you want to connect that to here, and the same thing applies. You want to make sure that the blue is on top and fits snugly into here, just so that this little clip kind of reacts to it a bit, and then flip it over. Oops. Okay, now it looks like it's good. So now you've got this connected, and generally the camera feed will show up like this. So if you have this placed somewhere, this is going to be upright. Oh, I need to connect our SD card. Let's move that over there. And last but not least is the DC barrel cable. So now we're ready to plug this in, and we can make sure that the camera's working. So here it is, put together. I've got it in my little Orange Pi rack here. It's really convenient to get one of these chargers that are meant for tablets. You can really slot the Orange Pis nicely in there. So it's running, and I've got the simple little GUI here, like the website, and this is the last frame that I grabbed from the site. I'll just refresh so you can see the picture of me recording. And the site also provides a live video, so you can see what the camera is currently able to see and what are the current predictions. This isn't the most interesting video because you can see me recording myself, so I'll just go back. I'm going to go now to the screen share, and I'm going to go into more details about this nice Grafana goodness. So here you can see the little web interface I put together for this. It's nothing special, but it's a small little Flask web app that reports the latest capture that the system has processed. Here you can see that, at least according to TensorFlow, I have a 71% chance of being human at this point in time. Maybe I'll refresh, maybe my humanity will have increased. No, it seems to have gone down. I guess that's what filming does to you. So while this is processing, the video stream is being processed on the Pi internally, and at the same time it's reporting nice metrics which you can graph with Grafana. So since I've just been recording myself making mistakes and then re-recording, this has been pretty stable. So you can see that the number of frames I've been capturing is about 0.8 because I've had it running on a lower frame rate to make it run a little bit cooler. And you can see that pretty steadily there is a medium or high probability or high confidence in there being a person in front of the camera, and we can graph this. I've had this running for a little bit of time. I think I can go maybe 15 minutes back, and you can see some of the other things that the camera had seen at that point in time. Here I think I had restarted the service. And yeah, so this is a lot of magic. So now how did this all get put together? Well, that's what we're going to get into now. So we're going to get into the gory details of how all of these things come together. So stay tuned, it's going to get technical. So here's a high-level view of what's happening under the covers. So we've got the camera producing a video stream, and we get frames from that video stream into our Flask Python program, and once we've got them there, we can then process those with TensorFlow, expose the metrics for Prometheus to harvest, and then we have Grafana there to make nice visuals. Let's take a look at the things that we're going to need to install on top of our base image. The most important thing to note is that the GC 2035 is not very well supported in newer kernels, so we'll need to go with a slightly older version of Armbian, which is based on a 3.4. You can see in the archive for Armbian, they provide some older images that you can use, and the one that we want is the one way here at the bottom, based on 3.4. So once we have that, I'm not going to go through this live because some of these steps take quite some time, but I've got the complete script here on the project page listing all the steps that have to be taken. So I'm just going to go through some of the more interesting parts of this. First and highly recommended is to use the custom version of the GC 2035 driver. Definitely recommended because it has a much higher image quality. The next thing you'll need is the GStreamer plugin for the Cedar hardware encoding device, I guess that's on the Allwinner chipset. This will allow you to grab frames from the GStreamer pipeline and feed them into the Python program, which is going to then process the image frames. The next thing is that we want to actually grab TensorFlow. So Google has very conveniently provided compiled versions of the TensorFlow runtime for ARM chipsets in a compiled wheel format. So you won't be able to do any training with this, but you will be able to run pre-existing models, which is exactly what we want to do. And this saves you a very, very painful compile of TensorFlow. Unfortunately, speaking of painful compiles, I am dependent on OpenCV for one very, very small tiny piece of the image processing pipeline, so I couldn't avoid having to actually grab the source code to OpenCV and compiling it because none of the versions that I was able to download that were binary versions worked very well. So unfortunately, this step takes quite a bit of time. The rest is installing Prometheus and some of the GStreamer packages that will allow you to process the video stream and the different steps of the pipeline. And then I have some links here for downloading Grafana and Prometheus. And if you're able to get through this script, you should have an image which is more or less good to go, and you're ready to actually run the program. So before I go into the code where we process the image frames with TensorFlow and all that, I thought I'd do a really quick demo of how we use GStreamer to connect to the camera and how it's processing these frames. And instead of showing you just some random code, I'll just do a quick demo at the command line with the GStreamer utilities. So I'm going to just SSH into the Lite right now. And so it's sitting over by me right now, and it's got the camera ready to go. And you can use GStreamer to do a lot of really cool things. So I mean, this one, I can just describe it at a very kind of high level, my best attempt to explain this. We've got a source device, which in our case is dev video 0. This is the video device that's set up by the video driver, the kernel driver for Linux. And then we specify some parameters about the type of video that we want to provide. This is the Cedar H20 or 26264 encoder. So these are a couple of stages in the GStreamer pipeline that you need in order to produce a video. And then the final interesting thing here, and so this is where GStreamer becomes really, really powerful, is that you can connect. So at this point, you can think of each of these exclamation points as different sort of stages, and then the final stage is typically a sync of some sort. And in this case, what we're saying for this sync, so I think this is now the orange Pi, and I'm saying the sync for all of these video frames I want to be host 192.168.0.14, which happens to be my laptop, and on port 5000, and sync this just so that we produce a faster video feed. And then what's going to happen with this is that this is going to now take image data from the camera, and it's going to start sending it on port 5000 over with UDP to this host. So as you can see, nothing is happening because it's just sending these frames, and then my laptop is not doing anything with the packets, so they're just getting discarded. So I can set up a UDP source. So this is source and sync are kind of like counterparts in GStreamer. So I set up a UDP source on port 5000, and then I say what type of payload I'm expecting, and then I have to provide a way of how I'm going to actually decode these packets. And then the final sync on the server, so on here, which is my actual laptop that I'm running this on, is going to be auto video sync. So this basically means just try to create some sort of a window that the video will be rendered into. So if I hit enter, you can see that there's me recording this video, and you can see that it's just basically sending the video over the network to my laptop. So that's basically the premise of how we're processing image frames within the context of this Flask application, except that the source, or sorry, the sync in this case here, so here we created a sync which is going to be a network host or with UDP, but in our case it's going to be a sync which will be a application sync, which is going to be our Python program. So here's our example of a Python program. In this case, a Python-based or a Flask-based web application. There you can see me. I'm looking at the screen, wondering why the detection seems to think my kitchen is a TV, but that's a whole other story. So let's actually take a look at the Python code itself to see how this integrates with GStreamer. So here you can see I've got this pipeline generation code, and this is part of the main worker thread that's handling all the GStreamer stuff on startup. So this is some boilerplate stuff, but the main interesting part is in here where we actually create the GStreamer pipeline. So if you remember from the example that we tried with the command line, you've got these different stages of the pipeline which are separated by these exclamation points. So we've just got the Python-based equivalent to creating this pipeline. So here you can see these objects which are created by the GStreamer code for the different stages. And the difference, of course, from the command line version is that instead of sending the frames over the network, we're going to send them to our application sync. So the application sync in this case is obviously our Python code. And here you can see that you can register a callback, which we've called onBuffer. So every time this pipeline, so the final stage of the pipeline would be this AV decoder for the 264. So this pipeline would send its raw data, more or less, to this callback. So this is your main interaction point with GStreamer. And so once you have this callback registered and everything is working, you can then do whatever it is that you want to do with the image data. In our case, we want to do object detection on it. So I won't go too much into the details of this because there's a lot of stuff here related to how we do counting of images and stuff, but effectively within this piece of code, you can extract the data, the raw data that you got from the camera, do counts or whatever other stuff that you want to do. And so with this raw image data, now we're going to pass this through our TensorFlow code, which is going to do the object detection. So I created a little Jupyter notebook here just to demonstrate what's going on with each of the image frames that we get from the camera. So you can see I've got the little library or module that I include with the program, and here I'm just going to initialize it with the MobileNet model, which we're using for this, because it's got a nice balance of accuracy and performance, given that this is a very, not exactly the fastest CPU that we've got on this Orange Pi. So I just got some, I've got an example of an image here of a nice spring scene in Toronto, and this is being returned in the pillow format. So this is a very, very convenient library if you're doing any kind of image processing with Python. And so this is our image, and then when we run the object detection on that image, we end up with a bunch of predictions. So in this case, these are just bounding boxes, so it's effectively little boxes that are the model has been configured to provide for things that it detects. And then we've got our little bit of code here, which is going to draw on top of that image. And then here you can see that it's done actually a pretty good job on this image. So it detected a bunch of cars. There's a person, there's traffic lights, and this is a streetcar, but I think a bus is a reasonable guess. So essentially this code here, this little notebook that we just ran here, this is happening on every single output of a frame from GStreamer. We run this, and then we also take note of all of this data about what class ID, so this corresponds to one of the labels that the model has been trained with, and this is what we're going to do on a continuous basis as this program is running. And here you can see the actual code that we're using to do this. So this worker, this is one of the configurable number of workers that spin up when we start the program, and this thing is set up to pull data off of a queue, so I won't go into the details of that, but effectively this worker is continually checking this queue to see if there's an image ready to be processed. It grabs the image. This is just being done to convert the image format into something that Pillow can work with, and we're going to run the exact same code that we just saw in the Jupyter notebook and spit out the result. And then we put this stuff back onto a queue, which is then going to be used to produce all those statistics. And so this is pretty much it. We can do this on an ongoing basis, and we make use of the 4 CPUs on the Orange Pi, and everything's great. So now that we've gone through how you can actually do the object detection against the live video stream, a natural question is to ask, well, how are we going to get useful information off of the box? So the way that I've gone about this is to turn the Orange Pi into basically a Prometheus metrics endpoint. So the Flask application provides a /metrics endpoint, which is a standard in the Prometheus world, and this endpoint is going to provide us some kind of like a sample of what's going on the box at this point in time. So if you're not familiar with the Prometheus format, this is kind of what it looks like. It's very raw data, and what happens is that Prometheus is configured by default to poll this endpoint on some interval. So I've configured this to poll every 15 seconds. So basically you can think of this as Prometheus is kind of like our database, and what it does is every 15 seconds it asks the Orange Pi, what are you seeing? And that gets provided by this raw data here. And so here you can see the one of the metrics here is the number of objects that have been seen, and what is the class, and what's the confidence, and the number of times it's seen stuff. So if you go into the actual Grafana endpoint, you can see what this is showing at the moment, what's actually being seen. So you can see that here, a person, that's me because the camera is right, pointing right at me. And then there's this TV. This is unfortunately, one of the problems that when you use one of these lower quality object detector models, it's frequently thinking that my entranceway to my kitchen is a TV, but that's okay. This is just a proof of concept in the end. So these are metrics which are being produced by Prometheus, and then we're graphing them with Grafana. So how do we actually do this in the code? It's actually fairly straightforward. If you use the Prometheus Python library, you can create counters, histograms, and other data types that Prometheus is aware of. In our case, a counter does the job. So I've got a couple here. So the more interesting one is this prom object scene. So every time we see a particular object, every frame that we process, we increment this counter for the object scene and the confidence. And then that's what you're seeing here. And then Prometheus is smart enough to increment this and to understand when something happened based on when this counter was incremented. And so that's how you're able to get effectively a snapshot at a given point in time. So as of this point in time, 3:05 at 15 seconds, it saw one TV and one person. I always find it amazing how powerful these little boards are, and before I started this little project, I never would have imagined Tensorflow would work as well as it does. So I hope you found this useful and interesting, and as always, relevant links are available in the description below. If you have any questions or want more details about how various parts work, feel free to leave me a comment. Thanks for watching, and so long.